Good day everyone and welcome back to the channel. So in the last video, when I got the amp going, I said that I wasn't going to make another video. I was just going to install these updated parts and then make a video of putting it together. Anyway, I reviewed my video uploads in this series of amp design and I noticed that there was actually something I left out, and well, there was a few things I left out. I've actually got 3 separate pages of stuff here to go over. So I was looking at compensation, 2-pole compensation, output inclusive compensation, traditional Miller compensation, and output inclusive 2-pole compensation, which is what we're going to do. And I was having a hard time working out, so I've drawn multiple scenarios. Basically, we've got our feedback line going back to our feedback side transistor, our resistor and cap to ground, our 22 puff 15k across our 15k, and that's the feedback point. Here we've got the beta enhance and the VAS transistor and another beta enhance and VAS transistor, both exactly the same. I'm just showing different things. So what we're going to do either way is add a 10 picofarad capacitor to ground coming off the collector of the VAS transistor. That's what these are for right here. Now, with normal compensation, you just have a capacitor going from the base, which I've drawn with these dots, right, to the collector of the VAS transistor. 2-pole compensation, C1 and C2 have to be, C1 say 470 picofarad, C2 will be 10 times smaller or whatever, 47 picofarad, and it will go to ground for 2-pole compensation. Output inclusive compensation, both the capacitors should be the same value, but it goes to a 560 ohm resistor to, oh, I drew that wrong. One moment. Someone's at my door, just give us a sec. Alright, my apologies. Is my focus locked? Oh, it wasn't. There it is. Alright, so let me just draw this correctly. I leave that here, and I'll still Alright, so output inclusive, you'll have C1 and C2 the same value, but you'll be going to 560 ohm to the feedback line. 2-pole compensation, like I said, 470 and 47 picofarad. It could be other values too, but for my amp, I've already done the math and everything. It goes to the 0-volt rail, so that's 3 types of compensation there. Now, before I go on to the next thing, I just want to touch on something from Douglas Self's book. I had it up on screen and it's lost the bloody page. And I do not have an absolute clue. Ah, man, if I have to pause the video and find this, I'm going to be pissed. I had everything ready for you guys. Ah, here we are. Okay, so when you're doing 2-pole compensation, as I stated in the last video, sometimes it's taken to the negative line, sometimes it's taken to ground. In my case, it will be ground. You get a mid-band peak, even with the capacitor ratio thing. And the solution for this is to add a 1.4 mega ohm resistor across C2. Just bear that in mind with what I'm going to show you here. output inclusive 2-pole compensation. So we still get our 10 puff from the collector to the 0 volt line. We still got C1 and C2, but the difference is now C1's going to be probably 100 picofarads and C2 would be 82 picofarads, or I might do 120 and 100. Anyway, that then goes to a 2K2 resistor to the 0 volt rail and a 2K2 resistor to the feedback line, which forms a voltage divider. So basically half of the compensation is getting fed to the 0 volt and the other half from the feedback line. So you've got your output inclusive compensation plus your 2-pole compensation, and it's traditional Miller at the same time because you've got, it's everything. It's kind of hard to explain. Yeah, anyway, a lot of people share different opinions on the way this works. I've done a lot of study on it. I can assure you I got this right. So my question was, what about output inclusive compensation? If 2-pole compensation, C2 plus 1.4 meg like this, what about output inclusive compensation? No resistor, higher resistor? Well, I thought about it. Normally, the 1.4 meg would, I'll just draw it in there. All right, 1.4 meg would go there. Now, what's it actually doing? It's going from the center point to the collector at the VAS. That basically goes through the bias string and into the driver transistors, and there's resistors between the bases. It all goes basically to the output, to the center point, which comes back through feedback. So essentially, you could think of it as like having a resistance to, there's basically effectively, because you've got a 2K2 resistor to ground and a 2K2 resistor to the feedback line, it's sort of like having resistance across this capacitor. So I don't think adding that in this setup will benefit it. And I did some research on this, and the values are slightly different. So you notice we've got, you know, the same value for output inclusive. For 2-pole, we've got a ratio of 10 to 1. With output inclusive 2-pole compensation, and this is what I've got to go back to the computer and show you more research now. Turns out if both the values are the same, there's a slight bump on the plot. When you make one, say 10, 20 puff bigger than the other one, C1, that gets rid of that. I have a feeling that's basically tying in with this resistance to ground and feedback and sort of creating the same effect as that 1.4 mega ohm resistor across there if it was just 2-pole compensation. I hope the way I've explained this has made sense. The beauty of this is the way I'm setting this up on board, which we'll get to after I show you the video, the pictures I've got. I'll have the options to experiment with different values and, you know, all of these options just by swapping a jumper around and values. So that's cool. So we don't have to just take these people's word for it and my research and all that and Doug's self. We can actually verify it. So now I'm going to go back over here. So someone built an amp using this topology. Okay, it's not as fancy as mine. You know, it's certainly not as fancy. There's a missing capacitor here. I guess this is just for simulation, but that capacitor is seriously going to affect it, I guess. But anyway, with 200 puff, and no connection. So just traditional Miller. So just, you know, basically there's 100 picofarads from there to there. That's what the waveform looks like. With 2-pole compensation, as I said, there's this mid-band peak, which I can show you a different graph, frequency versus, you know, I'm trying to say graph, and it shows the mid-band peak. And that's where you add the 1.4 meg across here, and it gets rid of that. And you've got the output inclusive compensation. It's mislabeled. Baseline is TMC. That is output inclusive TMC. That's what I mean. People don't understand the topology on this. Han, I'm working. Sorry about that. Anyway, so we see it's more rounded. So one way we've got a bump, the other way it's rounded, but the square wave response isn't as good as what it is just with traditional Miller. So then we have a look at both of them together and we see that, oh, okay, that actually looks kind of decent. And so then someone else, so notice this waveform. We've got the output inclusive two-pole compensation set up, but both the capacitors are the same value. And notice that the waveform is still only as good as baseline. Okay, it might be slightly faster, but it's not by much. Well, look what happens when we increase the capacitors, like I said, by 20 puff on one side. Hey? So, that's what we're doing. All right? I hope that makes sense. So, this circuit here, this is what I'm doing. 100 puff, 82 puff, because that works out to around about 45, 47 puff, which is what I'm aiming for in this amp. 10 puff off the collector to ground, and all the other values stay the same. All right, so that's what I've decided to do, is the output inclusive two-pole compensation to start off with. We'll see what the square wave response is like. If it is as it is shown on screen, I'm not touching it because it's perfect. And if there are bumps in it or whatever, then we'll start adjusting stuff and correcting it. But between what I've got on the computer and what I've got in this piece of paper, I basically know what's going on. So that's all the confusion taken out of that finally. Told you guys I'm very thorough. So the next issue that I've got, the emitter resistor on the beta enhanced transistor, it's 2K2. Originally I had a 470 ohm resistor and it got really hot, but it only got hot when I had the offset problem and it was pegged to negative rail. And that makes sense because, you know, if the current mirror is stuck down to negative rail and the output of the current mirror controls that, it's just pulling it down and it's just trying to sink all the current. Luckily, it's turning the transistor hard on, so that's not dropping current across it and getting hot, but the resistor is getting bloody hot, right? So, then my question was this. No. What do I mean by that? I abbreviate things and I forget what I'm talking about. Anyway, bigger transistor, lower resistor versus bigger resistor, smaller transistor. You know, here's the thing, right? The KSC 1845, its collector current's only 50 milliamps. Sorry, I knocked on my phone. So, you know, here's the other thing to take into consideration. You got your input stage. You know, I'm just drawing a very crude, you know, input stage here. I mean, you get the bloody current source symbol. You get what I'm saying, right? Your input stage comes into here. So what I'm trying to work out, I'm going to have to analyze this in circuit. How much gain is this producing and how much gain is this producing? Because, you know, say the whole rail swing around 33 volts is present here, then obviously the dissipation on here is a lot higher. If, say, this is only getting up to, say, 15 volts and the fast is picking up the other 15 volts, then there's only like 15 volts of swing on the base here. And remember, the transistor only conducts half wave, so the resistor dissipation is effectively half because it's a sine wave. So when it's positive, the transistor's on. When it's negative, the transistor's off, so there's no power. And that's what audio is. So say there's 33 volts, which I calculated the 2K2 resistor would work with. Well, I did that wrong because, like I said, the swing is only conducting halfway. So I could lower that to 1K, right? But if the swing is even smaller, like I said before, because there's gain here and gain here, that 470 ohms I had in there may end up going back in there. So I'll leave the 2K2 in there. We'll start it up. We'll measure the swing. And depending on what the swing is, you know, if it ends up being, you know, 15, 16, 17 volts a swing, 470 ohm will go back in there. And no, I'm not going to put a bigger transistor in there. I might go up to, say, like 100 milliamps collector current. You know, it's not going to probably make that much difference because the power dissipation of the transistor is going to be the same. So I'll probably just leave it. It's not the milliamps, it's the power dissipation that would be a problem when the transistor is actually in its active region, not fully turned on and dissipating the power through the resistor, which is not obviously happening all the time. But anyway, that's something else I've got to look at, but obviously that's after the amp is built. So that's two things to do before all the analyzation starts. Now here's the last thing I was thinking about. I want to see, with good cooling and good transistors, what I can get out of this amp. If power dissipation's too high at 63 volt rails and or 8 ohms, 250 watts, like, can this amp do an 8 ohm load and dissipate the whole, give out the whole 250 watts, or will it be too much for the transistors? I don't know. There's only one way to find out: do maths or test it. It's going to be close, so I'm just going to test it, and if it gets too hot, I'll know, and I'll turn it off before it gets cooked. Don't worry. Now, this is where I have done the math, because this is where my concern is. I'm designing this thing mainly for 4 ohms, and 250 watts per channel into 4 ohms is 31.6 volts, 7.89 amps per channel, right? Now, each amp module, which is it's 2 channels, it gets run off its own transformer. So the transformers, each winding's only got to supply that 7.9 amps. Now, I'd like to have at least double that or whatever for headroom and peak and all that, but you get what I'm saying. Now, at the moment I've got 63 volt rails, which means even when the amp's turned up all the way at full volume and the transistors are passing 31.6 volts RMS, the other 34, whatever it is, volts, 32.4 volts, are going to get dissipated on the transistor, if I'm not wrong, which means they're going to get bloody hot. So I was thinking, well, what about lower voltage power supplies? So if I got a 40 volt winding, like 40 times 1.35, that would give me 54 volt rails. If I've got a 32 volt winding times 1.35, it would give me 43.2 volt rails. And the reason I'm around 43 is because that still allows, see, 250 watts into 8 ohms is 44.7 volts, right? So what I was thinking is I don't need a 63 volt transformer to get my 250 watts into 8 ohms and my 250 watts into 4 ohms. So why do it? It's just more power dissipation. Obviously, I need headroom, say 7, 10 volts on top of this voltage here for sag, you know. But outside of that, yeah, 20, 30 extra 40 volts, that's just done. If I got a 36 volt transformer times 1.35, that's after rectification, what that is, 48.6 volt rails. I did the math. I'm happy with 54 volt rails. Because 54 volts, if you do the math, 44 to 54 it's just shy, because 0.7, it's just shy of 10 volts. Now, I'll be ordering a stout transformer, and I've got it on screen to show you. So it's not going to have much sag, because it's going to have low resistance windings that produce high current. So if I get the 40 volt one, they'll give me 54 volt rails. When my amp's putting out 31.6 volts, it'll only be 20 volts of dissipation, not 30 volts of dissipation. And when it's doing an 8 ohm load, which transistors are going to dissipate even more heat, right? It'll have 44, only 10 volts difference. And with sag, bugger all. Which means I might be able to pull off the 4 ohm and the 8 ohm load at 250 watts if I just choose my transformer correctly and, good heat sink and good cooling. So that was the third thing I wanted to touch on. And I've got the transformers. I've been looking on AliExpress. I know, don't laugh. I've done research. I've studied people who have bought these transformers, and basically the 1800 watt transformer, that's peak, not RMS. So it's only a 900 watt transformer. And some people had measured them and said that they were closer to like 700 watts, 800 watts. I don't think the people that gave the answers knew what they were talking about, because these guys have got all different transformers, like 1800 watt peak, 1200 watt peak, 500, everything. And in the reviews, some people were saying that they're great and showing photos of their projects, and you could see the windings look, decent. This is not the picture of the actual transformer, I can tell you that now. Unless it's really, really wide. It might be just really, really wide, because they've got some transformers that are close, like 1200 watts, and they're like this high, thick, but not as round. So I've got a feeling that's just wider than it is high. But that's the highest wattage one that they've got. And as you can see, I can get all these different rails. And that's why I was thinking, if I get, dual 40 volt, that would, and plus it gives the 12 volt windings that we need for the fan controller. The only problem with this is, whilst two of the transformers is only going to set me back $120, with shipping, it's $320. So if I decide to get them, it's going to be a few weeks before I get them. I can say that. So what my plan is I'm going to play around with those other transformers. The ones that I've got that I was going to boost the supply to, I'm going to try and run them at reduced supply voltages. I'm going to hook up the rectifier and the cap bank to it, hook it up to my load bank, and see how much sag I get compared to how much reduced line voltage drop I get. And basically, if it's doable to the point that I can just reduce the output voltage and still get the same current out of it on my load bank, I'll do that. Otherwise, I'll just run it how it is until these transformers come, and then swap them when they come. This also benefits me tremendously for the capacitor bank, because remember, I built the capacitor bank with 63 volt capacitors, and at the moment I've got 63 volt rails, which does not work. I mean, it will work, they're not going to blow up, it'll work, but I wouldn't run it like that for years, because it will shorten the life of the capacitors and destroy them slowly. But it won't be good for them. I like to at least have, 25 volts headroom on a capacitor, especially when it's on a rail that, it's got transistors on each side that are switching. You can get peak voltages across the caps and all that sort of stuff. You want bigger caps. I like to put 75 volt caps on 63 volt rails when I build amps, but this is what I had. So again, if I do this, 54 volts on a 63 volt cap, I'll be fine with that. So, yep, that's the plans that I wanted to go over. Now I'm going to show you what I'm going to do, like I said, I'm not going to show you building all this. I'll put it together and show you at the end of this video what it looks like, but I'm not going to make you watch me do it on camera because there's still a lot more to come. So for the output inclusive 2-pole compensation, this link right here that connects the 47 picofarad cap from the base to the collector of the VAS transistor, the link and the 47 puff are going to come out. The first cap that's going to go in is going to be, the first cap that's going to go in is 100 picofarads, and the second cap that's going to go in is 82 picofarads, and they go one there, one there. That link gets removed. Actually, one capacitor goes where that link is, sorry, and the other capacitor goes there. Then there's going to be a 2.2k resistor that goes from there to there, and a 2.2k resistor that goes from there to this provisional dual pad. And then what I'm going to do is I'm going to run a wire from audio ground right there off the star location on the end of that resistor over to that pad, and that will give us our 2-pole output inclusive compensation. So I hope everyone managed to follow that. I'm just going to go and get this done now and then just show you the finished project. Probably not going to power it up or anything. We already know it works. The bias is beautiful. It's all stable. There's no offset. It's absolutely wonderful. Heatsink was nice and bias warm. It was great. I already know that I don't have problems with output crossover distortion because I built this output stage earlier. I'd already done a lot of research on capacitor values. I got the crossover distortion down with 100 nanofarad and 200 ohms across the bases on the output devices, and 10 nano on here, and two 430 ohm resistors in series. So about 8, it used to be 820 ohm, but I put two 430s, so I've got a center point. More on that later. I'm going to, like I said, increase those 100 nanos to 1 mic and put the 100 nanos where the 10 nanos are. So there's not going to be any problems with crossover distortion with this amp. So basically just build it and then analyze it. If, like I said, the response isn't how I want it, we'll play around with this feedback circuit, get it how we want it. And then I haven't really told you guys this. I have said that I want to add regulation. I should be more clear on that. When I say regulation, it's probably going to be more like a capacitive multiplier, because what I'm aiming to do is not really regulate voltage so much, but remove ripple. Because your VAS transistors hung off the rail, a few things are hung off the rail, you got some bad power supply rejection ratio. Now, if you put a capacitive multiplier feeding these rails that feed the VAS and input section, you've got clean rails. So even if you've got bad rail rejection, problem solved. And it's actually quite convenient to do that with this board, because I split up the power traces like this. So I could put the resistors here and the diodes there and all that. I can take those resistors out and I can make a riser board on each side that's got a capacitive multiplier on it, and it would just output onto the 2 strips, pick up off of the input, and just have a wire that gets referenced to ground, which is right there. So I can literally just build 2 boards that sit there and there, sort of like this, and we'll have regulated rails. And if I want to be smart about it, because those boards are right where the power comes in, I could also add reference IC or something, a reference circuit. I might build a band gap circuit. I might build something more crude. I'm not too sure yet, but well, no, not crude, because we've already got something crude. So probably use a reference IC or something. So I'll make a couple of riser boards that will house capacitive multipliers and references, and then the current sources can have external references that won't deviate with the rail voltage. So in my mind, if the current sources can't deviate with rail voltage and there's no noise on the rails, that's a perfect amp. So that's the plans. So I'm going to go get the changes made that I've explained. I'll give you guys a look, and then I'll edit the video and I'll upload it. And the next video you guys will see will be putting this thing together and actually load testing it, and putting square waves through it at high frequencies and playing around with the compensation network, all that sort of stuff. So yeah, should get quite fun from here out if it's not already. All right, I'm going to get this done and then give you guys a quick look. You guys want to have a laugh at this? I've only changed the diodes, the bias diodes around the wrong way. I've only changed them on one board. And guess what? They're correct on the other board already. Somehow I just fitted them upside down on one board. Well, I'm cheering because they're an absolute bitch to get to. And I wasn't looking forward to changing them. I'll tell you the second thing I'm not looking forward to changing is this 100 picofarad cap that's across this 15k resistor, but because I'm going all out with it and I've got better ones, I'm going to change it, So yeah, I also like having variety of components in my collection. Like, that's the last of that style of 100 puff that I've got, but I've got plenty of these. I would still like to have some of those and some of those. So one day I want to do some comparison tests, or I want to use the smaller one for something because of looks, like I'm replacing something in an old radio, or there's just use cases, I like to keep variety, so I will swap them back. But yeah, I just thought that was funny. I thought I'd just point that out quickly, that the only modification I need to make other than adding the updates on this one is the resistors. So I've got to add two 68 ohm resistors. Have I wired this one up correct? Yeah, I did this one correct. So I need to just change these two 120 ohm resistors for two 68k resistors, and then set the pots to where those pots are set, and that'll do it. Those pots might look like they're all the way at the end of their travel. They are, but don't forget I'm changing. Oh, I do have to change the diodes still. Bugger. I'm changing 4 of the bias diodes, the ones that go back to the base of the transistor, for Schottkys. Because I figure if there is switching noise with the diode string, something I'm going to investigate is putting a snubber across just these diodes. Because I figure if I've got base resistors and Schottkys coming into the base, hopefully that Schottky diode and the base resistor might get rid of some of that noise, if there is any noise, from the diodes that are on top of the heatsink. And I'm thinking, if that's not perfect, maybe putting some sort of snubber across the diodes on the heatsink in conjunction with the two Schottkys and the base resistors should make it perfect. I mean, the SAP 15, SAP 10, SAP 8 devices, they just use PN junction and Schottky junction diodes in their bias string with nothing but a 200 ohm pot in the middle of the string. And those are some extremely low THD linear devices. So, I mean, if I can improve on that, winner, winner, chicken dinner, right? Something I just wanted to go over quickly. This 100 nano cap that I'm going to make 1 micro, I remember before playing with in between 100 nano and 680, and I think 680 was better. I can't remember, but I've seen people go anywhere from 100 nano all the way up to 1 microfarad, and in all the blameless designs, it's 1 microfarad, and those amps are running off 37 volt rails, producing 100, 150 watts, sometimes even 50 watts. So this is a much beefier amp with higher power. So that I feel 1 microfarad is going to be the correct value to put here. I just wanted to go over why I believe that. Also, I have fitted the 68 ohm resistors. So it's the same on both output stages. Now I just need to turn these two pots, all the way in. The way it is at the moment, the bias is basically set perfect with the pots all the way closed, but because I've just changed 2 of the diodes, well, a total of 8 diodes, that bias is going to go back up again, which means the pot's actually going to end up in the middle, which is where we want it. So it's got range either side. So that's going to stay exactly how it is. That's perfect. So I'm going to change these caps now. I'm not going to keep going back every time I do something, unless there's something that I want to point out that I think that I might not have explained why before, then I will, but other than that, I'm just going to continue working. I just want to talk about something. I just got these Beamers in here. The reason why I've always been so fussed over the value of these 2 resistors, the capacitor there, and the same for the driver stages, those caps and the 430 ohm resistors. Cross distortion is something I don't see talked about very much. I see crossover distortion talked about a lot, but not cross distortion. And I once took an amp, a stock Denon amp, plugged it in, and hooked my signal generator up to the input and the power meter up to the AC plug. Now, don't get me wrong, I understand the Zobel network obviously is dissipating power at higher frequencies, but as I turned the frequency up and turned the amp's power up, the power consumption of the amp went up a lot. I then decreased the value of the base sucker resistors and increased the value of the caps, ran the test again, and the power kept linearly decreasing. I obviously had to keep adjusting the bias because that kills the bias too, but point is, cross distortion is something that I've found is even overlooked in relatively high-end amps. Everywhere I look on forums and stuff, I see some people talk about it for like 2 seconds, but it's just not something that people seem to, I don't know, realize exists, understand the issue with it. See, the issue with cross distortion is what's happening is at high frequencies, the bases don't have enough time on the PNP side and the NPN side to discharge and turn off fully, which means for a short period of time, both transistors are on, conducting current into each other through the emitter resistors. And I don't mean bias current, I mean considerable current, which is bad for 2 reasons. 1, it can destroy your output devices. 2, it's a waste of power. Well, causes more heat too. There's a myriad of reasons. Distortion at high frequencies. It's just, it's a massive thing, and I just don't understand why it's overlooked. So I just wanted to come on and talk about that for 2 seconds. But anyway, as it is, that is all the components fitted to the output stage. I've started removing stuff off these boards. So mainly just the polystyrene caps, because I've got a habit of bumping my soldering iron into them. So I figured I'd take them off first, do all the other stuff, took the diodes off because they're the hardest to get to. So I've got the diodes formed up, the BAT 46s, 46 or 48 I chose. I chose them because of the milliamp rating, the forward voltage, and the capacitance. BAT 46. I was looking at BAT 42, BAT 46, BAT 48, 5711, 5819s, 5820s, all that sort of stuff. And BAT 46 was the best in terms of a Schottky for this application. So I used it. I've got my 100 nano caps to swap over here. They'll fit in there just. So I'll get all this done now and then come back and give you guys a look. Something else I just wanted to touch on quickly is these capacitors. So these have got a lower ESR than the Mylars. I measured it at 1 kilohertz. The Mylars are 8 to 9 ohms. These are about 6 ohms. So quite a bit lower. And when you're down at like 100 hertz, these are still I can't remember what it was, but it was still lower than the Mylar. Like the Mylar went up into like 70, 80K or maybe hundreds of K. These were still at like a K or hundreds of ohms. I can't remember, but they were miles better, right? Now, here's the thing. You got to be careful doing this. If I was to say use MKTs or something that's like 0.01 of an ohm at 1 kilohertz, I'd actually be defeating the purpose here. Because these capacitors, what these are doing is they're actually getting rid of noise off the rails. And having a bit of internal series resistance, a few ohms, gives them a damping factor, the same as if you were to make an RC snubber. Now, if you use caps with a too low ESR, you'll actually lose that damping factor. So, and then you would have to, you could make up for it by adding a series resistor, but why do that? You just choose the right part. That's why the power supply cap bank is made up of electrolytics and MKTs with a really low ESR, because that's there to provide current at low and high frequencies. This is here to decouple noise. So just think about that when you're designing stuff, you know. I did improve it from Mylar to this, but you know, if I went, say, lower in ESR than this, I would be then defeating the purpose. This is basically the best you're going to get for this purpose. And if you go have a look in a lot of amplifier designs, especially Yamaha stuff, this is exactly the capacitor that they use for exactly what I'm talking about. They even use them for audio coupling too. Philips actually makes some really nice versions of these. They're actually orange. I don't know if they're still in, get manufactured these days, but I've actually got some. I'll show you in a sec. Mine are old board pulls that came out of older equipment, but absolutely beautiful capacitors, beautiful quality. But yeah, basically that's what these are, just not Philips. I'll just go grab some. I've got smaller ones too, but these are what I'm talking about, and on the top of them they say what they are. MKT. Actually, those don't say Philips on top. I've got some that are Philips, but they might be, I'm not sure. But yeah, I don't know why there's an electrolytic in there. Oh, I see, that's jumped out of there. Anyway, I just wanted to touch on that quickly. As you can see, I've got everything fitted. I've just got to fit these now to both boards, and then I'll come back and do the compensation stuff on camera, because I wanted to talk about that. I just didn't want to bore you guys watching me fit all the capacitors and diodes and all that sort of stuff, but as you can see, it's all in there. Alright, well, that is finally everything thoroughly gone over 2 or 3 times, and I've made sure that, you know, I've done everything as good as I can do. So the output stages are all finished, as you know, all the upgraded parts that I've added. Both of those are ready. Bias strings are ready. These 2 boards now have the Schottky bias string diodes, the MKPs, the 100 nanos. What series are these? Nichicon. All the capacitors on here are really nice caps. Like the rail caps are Nichicon FW Gold series. These are Nichicon PWM series. These are VRM series Nichicons. These are ZLH series, because that's in the feedback area. As you know, these are audio crossover capacitors made by MTL, a company that specifically makes audio capacitors. You know, there is no cheap capacitors on here. Some of the capacitors would cost you like, you know, $10 to go buy just singly in a store. So yeah, anyway, that is all that done. I've got the decoupling caps here right in between the 2 emitter connections to the rail, decoupling it to ground, and on the positive side as close to the resistor to the current source and to the ground rail. Obviously, location is everything. That's something else people don't realize. This is why I design my stuff. My stuff might look a little bit different to everyone else's work, let's just wait until it's all finished and I've got equipment, and then I can brag about it and say, hey, this is why. You'd be quite surprised, even with a trace this thick, the difference between putting that capacitor there and down here. I mean, you could increase the gain on this input stage to say something stupid like times 100. Hook a speaker up to the output of it. Take the high pass filter, high frequency filter cap off the 15k to ground resistor. Listen to the hiss and noise, and move this capacitor further down the rail, and you will literally hear it getting louder. And you know, we're talking tens, if not hundreds of a milliohm of difference of track. You'd be quite surprised. So yeah. Anyway, what we're up to now, and this is what I wanted to just give you guys all a look at, because as I've gone over, I wanted to show you the paper again, but I don't have it in me to move the paper. The 2-pole output inclusive 2-pole compensation, whatever you want to call it. It's traditional Miller. It's traditional Miller compensation. I'm going to come up with my own term for it. Output inclusive 2-pole Miller compensation. Not traditional, because it's not traditional, but there is still capacitance between base and collector, so there is still Miller, traditional Miller effect going on there too. So yeah, the best of everything. The only thing I have yet to experiment on is the value of C1 and C2, and putting a resistor across C2, and also, you know, taking the resistor just to ground, just to feedback, or having it divided to both. But like I said, if this works exactly as it's supposed to, and the waves are exactly how they're supposed to look, I'm not going to touch it. I'm going to play with it if it's not the best thing in the world. What am I doing? I've got to form up components. So what I'm going to do now is basically 2.2k resistor is going to go from the feedback to that pad, and from that pad to here, and then one of these green wires will go to the ground, to the other end of that pad. Incidentally, this is the last of this particular, like, exact type of green wire that I've got. I had in my scrap box, and I went through it and had a look, and I was like, oh wow, cool, because I can use the exact wire, which is nice. This isn't the cheap crap that you buy at like Jcar, stuff like that, that's, you know, like got really small conductor size inside it. This is I don't know, maybe 18 gauge or something, maybe more. I don't know. It's I could go get, actually, let me do this because it's actually quite funny. Yeah, Jcar, and I'll see you this, right? Right, that's the conductor size of that. Now, bear in mind, the green wire is physically smaller. So let me take my focus lock off. You know, this is the thing about me. I'm all about quality. You might not notice on camera, but everything I select, I really, really carefully select, you know, like down to wire, literally. So anyway, I'm going to get this fitted, and then I'll come back and show you, because me just trying to explain where everything's going to go is probably quite annoying. So I'll just fit it and then come back and explain it. I've also angled all the transistors back just a little bit. Two-part reason. One, well, not that these capacitors will really get damaged by heat, but their capacitance value will change with heat a little bit, so it's still not recommended. Honestly, it's more for the transistors cooling, because they're going to dissipate heat. Heat rises, right? So if you've got a surface that's got that much area facing up as opposed to that much area facing up, that's going to dissipate heat quicker. So if you lean them over, they dissipate better. Also, I've tried to space them sort of in between the electrolytics so that they're not too close to electrolytics, because heat will cook those. Anyway, I will get the rest of the this output inclusive Miller 2-pole compensation done, and then give you guys a look. And then it's finally building time. Well, actually that's a lie. I've still got to do one thing. I need to get the transformer, hook it up. I got to do some tests on, can I make these transformers, I might change the winding ratio on them if I can be bothered. I don't know. I got to do some tests. I got to load them down, see what voltages I can get out of them with what input configurations, boosted, unboosted, bucked, whatever. Because as I said, I might buy other transformers. I'm not too sure. The other thing is, like I said, I've only got 63 volt caps on the cap bank, so all the caps on this board are all 100 volt caps, except for the caps that are in the bias network and stuff like that, and the 16 volt cap that's in the feedback network to ground. But all the caps that are reference voltage in between rails, they're all 100 volt caps. So it's just the cap bank, but I've still got to work out what I'm going to do about the power supply. So I might do a video on that, setting it up, loading it, trying different arrangements, working out what we're going to do. Worst comes to worst, I do have those huge honking 100 volt, what are they, 10,000 mic? Yeah, 10,000 mic. I've got like 8 of these or something ridiculous, so there's no problem. I can make this work however I have to do it. It's not like I don't have the capacitors. I was going to save these for a much bigger, more powerful amplifier that had, 3 or 4 parallel output devices per channel, NPN and PNP, so like a total of 6 or 8 devices per channel. I was going to save these for a build like that, but I can always buy more. They just sell them at JCar. It's just that they're a bit expensive, but they are a great capacitor. They are big. I mean, you get what you pay for, right? So we'll see what happens. The worst thing is, dumbass me, you guys won't believe this, I used up almost all of my 4700 mic 63 volt caps on this build. So I went and ordered a whole lot more, and you know what I did? I ordered 63 volt 4700 mic, still 63 volt, like what I was running out of. If I had been thinking, I would have got 75 volt or 100 volt. I mean, it's all good. I've got plenty more amps to build. It's all going to get used. And with the way I build my cap banks, those numbers diminish quite fast. Alright, I'm going to get this done because otherwise I'll just keep wafting on. And then I'll give you guys a look. And there you go, ladies and gentlemen. Output inclusive 2-pole Miller compensation. So we've got 100 picofarads, 82 picofarads, 10 picofarad from the VAS collector to ground. Over here we've got the 22 picofarad. I've put these 100 picofarads in as well. It's all done. That's what it looks like, and I've run the extra ground wire across to bring ground over to the 2-pole compensation, half of the output inclusive 2-pole compensation. But yeah, also I found that one of these capacitors was connected to the wrong pad, so I corrected that. But yeah, and I cleaned up the solder off of a few spots. But yeah, it's finally finished. That is all the upgraded components on there. I have nothing else I plan on doing to this in terms of upgrades, apart from one experiment. As I've said before, I'm curious about putting a snubber across. Well, it would have to go across from there to there and from there to there, because that's one string and that's the other string, respective of the transistors that they're above. We'll see how the thing performs first. If the performance is literally just through the roof like it should be, I probably won't worry about it. I've already added shotkeys on the end. There's base resistors after that. There's this nice cap across it. There's a 10k resistor across that. You know what I mean? It's probably fine. So that concludes that. So the next video, I'm going to work out what's happening with the power supply, because as I said, I wouldn't mind getting 40 volts, 54 volt rails. So we'll see what I can do with what I've got and what capacitors, and then the video after that will literally be putting this thing together in the case, loading it. I might actually put it together on the bench, just one board and one output stage and one transformer, and load it like that first before I put it in the case, just in case something unforeseen happens, and do the testing first. But yeah, power supply, load testing and all that sort of stuff. Alright, well, thanks for watching, everyone. Oh, and also, yeah, it was hard getting these MKP CYOG caps in there, but I managed to stand them up and get them in there. Anyway, that's it. I think they look beautiful. Alright, I'll see you all soon. Thanks for watching.